Okay, so we're going to start our lesson on Extrema by taking a look at pages 89 and 90 in the textbook, which is where this comes from. And I'd like you to pause the video and just read through this text and this definition about local and absolute extrema, and then try to understand it. And when you're ready to resume, turn the video back on and we'll read through it together. Okay, so hopefully you've taken a second to read through this text on your own. Now we're going to read through it together. Many graphs are characterized by peaks and valleys where they change from increasing to decreasing and vice versa. The extreme values of the function, or local extrema, can be characterized as either local maxima or local minima. The distinction can be easily seen graphically. Figure 1.24 shows a graph with three local extrema, local maxima at points P and R, and a local minimum at Q. So I'm going to pause here for a second and take a look at this graph in figure 1.24, and we can see here that it's increasing until we reach point P, and then it's turning here and starts decreasing. So P is a peak or a local maxima. Okay, then as it's decreasing, it keeps going down, down until we hit point Q, and then in this valley, it turns to increasing, so decreasing to increasing, and that turning point is a valley, and that would be a local minima. Okay, then at R, we have another peak here where the graph changes from increasing to decreasing, and so that would be another local maxima. Okay, they're local because it's only over one particular interval of the graph where it is a maximum. So for example, R is the absolute highest point on the graph, so R would be an absolute maximum, but between 0 and 1, on the x-axis here, we can see another maximum, but it's just a local maximum to that interval, right? It's not the highest point ever on the graph because that's up here at R. Okay, Q is a local or relative minimum because it is a low point, but not the absolute lowest point, because you can see here that this end of the graph continues going down lower. So Q is a local or relative minimum. Okay, so back to the text. This is another function concept that is easier to see graphically than to describe algebraically. Notice that a local maximum does not have to be the maximum value of the function. It only needs to be the maximum value of the function on some tiny interval, right? So we have, like we said over here, a local maximum from 0 to 1, and another maximum, a local maximum here between 3 and 4. Okay, we have already mentioned that the best method for analyzing increasing and decreasing behavior involves calculus. Not surprisingly, the same is true for local extrema. We'll generally be satisfied in this course with approximating local extrema using a graphing calculator, although sometimes an algebraic confirmation will be possible when we learn more about specific functions. And in calculus, when you get there next year, you're going to learn about derivatives, and derivatives are where these turning points and these extrema, also called critical points, these are going to be important when you have derivatives, because where the derivative equals 0, right, that's how you know that there's a special critical point going on. But for this course, because we're not talking about derivatives yet, we're just going to be focusing on looking at the graphs, classifying the extrema as relative, local, or relative, they mean the same thing, or absolute extrema. And we're going to do that primarily with a graphing calculator. If you don't have a graphing calculator, Desmos or GeoGebra, those would be fine as well. Okay, so the book follows then with this algebraic definition of local and absolute extrema, where it says a local maximum of a function f is a value f of c, where c is just some constant that we're putting into the function, right, that is greater than or equal to all range values of f on some open interval containing c. if f of c is greater than or equal to all range values of f, then f of c is the maximum or absolute maximum of f. Okay, so when we look at this graph, R, this point R is the absolute highest point on the graph, right? That would be an absolute maximum. Okay, P is just a local or relative maximum because it's a maximum between 0 and 1, but not the highest point on the graph. Okay, then the definition goes on to say a local minimum of a function f is a value f of c that is less than or equal to all range values of f on some open interval containing c. If f of c is less than or equal to all range values of f, then f of c is the minimum or absolute minimum value of f. So the Q here is a local minimum, right, because it is a low point, but it is not the absolute lowest point, right? So it's not an absolute minimum, it's just a relative or local minimum. And you can see down at the bottom, local extrema are also called relative extrema. So those are synonyms. You can call it a local minimum or maximum or a relative minimum or maximum. Those are interchangeable. Now, this algebraic definition is very difficult generally for students to comprehend at first. It takes quite a bit of analysis to really understand what that means. So in the notes on the front of the booklet, when we're asked to talk about what is relative extrema and absolute extrema, right, paraphrase what we just learned in the book together on your notes. You don't need to use my definition. This is just my way of paraphrasing it. You can word it however you want to, but you want to get at that idea that a relative extrema, which remember is also called a local extrema, right, is the y value of any point where the curve changes direction from increasing to decreasing or from decreasing to increasing. Okay, it cannot be an end point, however. Okay, so it's only when it changes direction. So it could be a peak or it could be a valley, right? That would be a local or relative extrema. Okay, now absolute extrema, that is when the y value at the highest, the absolute highest or absolute lowest point on the graph, it can be an endpoint, but not infinity or an asymptote. So when we get to some examples with rational functions where we have values approaching positive or negative infinity, or approaching a horizontal asymptote, those are not considered absolute extrema. Okay, only the absolute highest or lowest points, not what in calculus we think of as limits. Okay, we're not going to be looking at limits with respect to our extrema. So in this context, right, your absolute extrema would be something like this, where you have an absolute highest point on the graph. That would be an absolute maximum. Okay, this point is both an absolute max and a local maximum. This would be local only, right? Not an absolute maximum. And this would be a local or relative minimum. Okay, so again, to be absolute, it has to be the absolute top of the range, right, of the y values that are possible. That makes it an absolute extrema. Okay, so in example 1, we want to identify the absolute extrema, remembering that an absolute max is the absolutely highest y value on the graph, and absolute min is the absolute lowest y value on the graph. Okay, at this point, we're not going to worry about identifying any local or relative extrema, just the absolute in these pictures. And we want to take note that infinity and asymptotes do not form any kind of extrema. So in examples A and B, the graph is given for us. So we're just going to take a look and analyze this graph. And we see 3 turning points, right? There's one right here, another here, and another here. So this one in the middle at 0, -1, that's a relative maximum or local maximum. So since we're only identifying absolute extrema, we're going to ignore that for the moment and instead take a look at these 2 points here that both have the same y value of -3.25. So that would be the very lowest possible value in our range, which would make it an absolute minimum. So this graph has an absolute minimum of -3.25, right? That's the y value at that lowest point. Okay, then go ahead and pause the video and try example B, and then you can resume when you're ready. Okay, so in example B, hopefully you've given this one a try. We have an absolute lowest y value here of -4. Okay, so that will be our absolute min of -4. And then our highest y value is -1 at the top of this semicircle, and that would be our absolute max of -1. Okay, so now we're going to take a look at example C, where we're asked to use transformations now to sketch this graph. So since it's a square root function, we know it makes half of a sideways parabola that has this general shape. Okay, and then this 2 in the front, that's a vertical stretch of 2. The +3 here is going to give us an h of -3, so it's going to move to the left 3, and then the k is -4, so it goes down 4. So we're going to start at the origin where the parent graph's endpoint would be, and we're going to go to the left 1, 2, 3, down 1, 2, 3, 4, and that point at -3, -4 is our new endpoint. Then using that vertical stretch of 2, we're going to start at the end point and go up 2 and to the right 1, and then that gives me another guide point. Okay, then to get a more accurate idea of where to turn here, I'm going to pick a value for x that gets me a nice perfect square. So for example, if I put in 1 for x, 1 + 3 is 4, square root of 4 is 2, times 2 is 4, minus 4 is 0. So 1, 0 would be on this graph. Okay, then if I were to put in 6 for my x, 6 + 3 is 9, square root of 9 is 3, 3 times 2 is 6, minus 4 is 2, and 6, 2 would be on this graph. And then I can hopefully not make a mess here. Let's see if I can sketch this. There we go. Okay, and that would be my square root function. F of x equals to square root of the quantity x + 3 minus 4. So this graph has an end point here at -3, -4. So my absolute extrema is going to be an absolute minimum because it's the lowest point in the range of, and then my y value is -4. Okay, so this function has an absolute minimum of -4. Okay, go ahead and pause the video then and use transformations to sketch example D here and identify the extrema, the absolute extrema, without using a graphing calculator, just transformations, and then resume when you're ready to check. Okay, so welcome back. Hopefully you took a second to graph example D using transformations. This is an absolute value function, so its parent graph is a V shape, and its vertex would be at the origin, 0, 0. Okay, this negative in front, that's a reflection in the x-axis, so that's going to flip this absolute value graph upside down. Then x minus 1 means my h is +1, so I go to the right 1, and then k is 2, so we go up 2. So starting at the origin, we're going to go to the right 1, up 2, that's my new vertex at 1, 2, and that negative flips my v upside down, and that gives me anchor points at 2, 1, and at 0, 1. And absolute value graphs, they're straight coming out from this vertex, these two rays, so we can follow that same slope in both directions, and then we can use that to sketch the graph. So let's go ahead and go this way, and then that way, and there's my graph. Okay, so now I can go ahead and identify my absolute extrema. This is maximum now because my range is from -infinity to 2, including the 2. So 2 is my absolute maximum. So I would describe this absolute extrema as an absolute max of +2. Okay, so on some scrap paper or on an individual whiteboard if you have one, I'm going to ask you to pause the video and go ahead and identify any absolute extrema for each of these graphs. Okay, we're not worried about the relative extrema at this point, just identifying and classifying your absolute maxes and mins. Okay, and then when you're ready to resume, you can turn the video back on. So in example A, okay, we have no absolute extrema because we can see that this graph is going up forever and down forever at these ends. These two turning points in the middle here, these are relative or local extrema, not absolute. Okay, in example B, there's a local or relative minimum here at 3, but the absolute maximum is up here at 4. So there's an absolute max of 4. Okay, in example C, this one is, we can see a rational function. So it had vertical asymptotes at -3 and +3, shaping that graph. Here's our horizontal asymptote at 2. And we can, if you remember in the notes, we cannot count horizontal asymptotes as extrema. So this graph only has only has relative extrema. There's a relative maximum here at 1.5, but it's not the highest point on the graph because these curves are extending up forever towards that vertical asymptote, and so this graph has no absolute extrema. Okay, in example D, these are endpoints here at 4 and -4 on the x-axis, so the graph is not extending forever in either direction, right? It's fixed between this domain of -4 to 4 inclusive. So we've got an absolute maximum of 8 and an absolute minimum of -8. Okay, in example E, this is another rational function. So we can see the graph being shaped by these vertical and horizontal asymptotes along the x and y axis. And recall, asymptotes do not count as extrema, so this has got no absolute extrema or relative extrema. And then in example F, this is a square root function, and it's got an endpoint here at -3, 6. That endpoint is an absolute minimum of 6.